Assalamu alaikum. I'm Phy213, affiliated with the Department of Physics at the Kust202 University of Science and Technology in Pakistan. This lecture is recorded as part of an undergraduate course, Phy213 Fluid Mechanics, offered at the Kust202 University of Science and Technology. This is lecture 9 of this series, and the title of today's discussion will be Speed of Sound and Mach number. By the end of this talk, you'll be able to relate the speed of sound and a fluid medium, especially gases, to the macroscopic properties of the medium, such as the temperature and the variation in pressure with respect to density of the medium. You will also be able to compute the Mach number of a fluid, especially gases, having certain speed at certain temperature. The textbook that we follow is the Fluid Mechanics Fundamentals and Application by Yunus Shangel and John Simbala. This is the 4th edition. There are certain other books that could be referred to. Some of these books are shown over here. This lecture is outlined as below. We will have a brief recap of the previous 2 lectures. That will be followed by the discussion on the speed of sound, and we will be working out a relation for the speed of sound and a fluid medium. Then we'll introduce Mach number, and that will be followed by then the recapitulation of whatever we discussed today. And then we'll solve one numerical exercise that could be used as an example for the other exercises and problems that would be presented to you during this course. And at the end, we will have one slide about the contents of the next lecture. Let us recapitulate the energy and specific heat terms that we have learned in one of the earlier lectures. The total energy denoted by E is the sum of the macroscopic energy and the microscopic energy. The macroscopic energy is equal to the kinetic energy, which is proportional to the squared of the velocity, and the potential energy, which is proportional to the distance or height z. The microscopic energy is the internal energy or heat of the system. If the fluid is flowing, then the microscopic energy is referred to as enthalpy H is equal to the internal energy, and an additional term, the flow term, which is equal to PV, or which is equal to P over rho. So if we write down the total energy E in terms of the enthalpy H and the kinetic energy term, which is proportional to the square of velocity, and the potential energy term. The specific heat of an ideal gas at constant volume is equal to the differential of the internal energy U with respect to the temperature T. If we want to take the average of the specific heat, then that will be the finite difference of the internal energy with respect to the finite difference of the temperature. Similarly, if we look at the specific heat of an ideal gas at constant pressure, that is equal to C subscript P, which is equal to the differential of the enthalpy H instead of the internal energy with respect to the temperature T. If we take the average, then the differential is changed into the finite difference. So the finite difference and the enthalpy H with respect to the temperature is equal to the average specific heat at constant pressure. The coefficient of compressibility kappa is equal to minus V del P or curly P or curly V at constant temperature T. And this could be written down as rho and del P or del rho at constant temperature T. If the changes are finite, then kappa could be written down as approximately equal to minus delta P or delta V or V, which is the difference in the volume per unit volume, which is the frictional change in the volume. So kappa is approximately equal to the change in pressure or the frictional change in the volume, and this could be written down as the change in pressure or the frictional change in the density. If the fluid is an ideal gas, then kappa is equal to the absolute pressure P. So now if we combine the kappa ideal is equal to P with the kappa is equal to delta P over delta rho or rho, we get delta P over P is equal to delta rho over rho. The other term which is quite useful is the isothermal compressibility alpha, which is equal to the inverse of the coefficient of compressibility kappa, and this we can write down by using the equation for kappa is 1 over rho del rho over del P at constant temperature T. The coefficient of volume expansion beta is given by 1 over V del V over del T at constant P, and we can write this down as minus 1 over rho over del T at constant P, and the dimension of beta is the inverse of the temperature T. So if we have finite changes, then we have beta is approximately equal to the frictional change in volume divided by the change in the temperature T, or this is equal to minus the frictional change in the density over the change in the temperature T. In case of an ideal gas, beta is equal to 1 over the absolute temperature T. So if we combine beta is equal to 1 over T with the finite changes relation of beta is del rho over rho over del T, we can have delta T over T is equal to delta rho over rho. When we have natural convection, then density at infinity minus density at ordinary point will be equal to the density at that point and to the volume expansion beta and the change in the temperature. So if we have the expansion as well as the compression, that is when the volume is a function of temperature and pressure both, then we have the frictional change in volume is equal to the frictional change in the density, and this is equal to beta into delta T minus alpha into delta P. Now let's start with the speed of sound. Consider a duct containing a stationary fluid. The duct area of cross-section is A, and it has these parameter. H is the enthalpy of the fluid, P is the pressure, and rho is the density. If the duct is fitted with a piston, by applying a force onto the piston, we will be able to push the piston inward to a new position shown over here, and this will cause a velocity change del V or dV, and this will create a face front, and this face front will start moving with certain velocity c. Because of the motion of this face front and because of the movement of the piston at this end, we will have change in the pressure and change in the enthalpy, consequently change in the density. So the small change in the enthalpy is dH, and that is also causing a small change in the pressure, which is dP, and consequently the change in the density is d rho. So the density, pressure, and enthalpy on the inside is H plus dH, P plus dP, and rho plus d rho respectively, whereas on the outer side this fluid remains stationary, and we have enthalpy as H and pressure is P and the density is rho. If we look at the graph, then we have caused a change in the volume from this point up to the point of the wavefront, and this change is dV, and after this point there is no change in the velocity. Similarly, if you look at the pressure, then till the point of the wavefront we have the change in pressure dP included into the total pressure P, while after the phase front we have just the pressure P. So now, instead of looking into the general picture of the duct, let's start riding on the phase front. Now in this case we'll see that the fluid on this side will be moving with the velocity c, whereas the fluid on the other side is now moving with the velocity c minus dv, because now the recording is on the phase front. So if we use the conservation of mass, there's no change in mass, so the change in mass on the left is equal to the change in mass on the right. So m dot right is equal to m dot left. If we put the values of m right, this will be equal to the density into the area into the velocity. So the change in the mass is equal to the change into the volume. Basically C is reflecting the change in the volume because rho is constant and A is constant at this side. On the left side we have the change in the mass is equal to, now we have a change density rho plus d rho. The cross-sectional area remains constant, but now the velocity has been changed to C minus dV, as can be seen over here. So now if we expand this term and then neglect the second order term and dividing by the cross-sectional area A, both sides of the equation, we get C into d rho minus rho dV equal to 0, and this we can write down as C square d rho over rho is equal to C dV. Let's say that this is equation A. C d rho minus rho dV is equal to 0 from the page before. So if we have steady flow energy balance is then adiabatic propagation, then the energy N is equal to energy out. With no change in the potential energy, we have the enthalpy, which is the internal energy, plus we have the kinetic energy C square over 2. This is equal to the enthalpy on the other side, which is H plus dH now, plus the velocity term C minus dV whole square over 2. Once again, neglecting the second order term, we get C dV is equal to d. Ordinary sonic waves have small amplitude. They cause no appreciable change in the pressure and the temperature of the fluid. And the whole process is nearly asymptotic. That would imply that the density, the entropy remains constant. And if you remember, enthalpy H was equal to the internal energy U and the flow energy PV. Taking the differential, we can write this down as du is equal to dH minus PdV minus VdP. Also, if you remember, we had the change in the internal energy was related to the change in entropy and the work done because of the change in the volume. So du is equal to TdS minus PdV. And rearranging this, we can write down TdS is equal to du plus PdV. Combining 1 and 2, we can write down TdS is equal to dH minus VdP. Or TdS is equal to dH minus minus dP over rho. So V is replaced by 1 over rho. Now in this equation, since we are saying is that the process is isentropic, that would mean there's no change in the entropy. So ds is equal to 0. So we have dH is equal to dP over rho. Using the relation that we have earlier derived, C dV is equal to dH. So putting the values of dH into this relation, we have C dV is equal to dP over rho, or putting this value of C dV into the early equation A, which was C square d rho over rho is equal to C dV. So we have C square d rho over rho is equal to dP over rho. Rearranging this equation, we arrive at the relation for the speed of sound in a fluid, which is equal to the differential pressure with respect to the differential density at constant entropy. So this is the square root of del P over del rho at constant S. Now let's look at the two different cases. One is the isothermal process where we keep the temperature constant. Another one is the isentropic process where we have the entropy constant, or where we have the adiabatic process with the reversibility in place. Now in case of isothermal process, we have the famous relation that PV is equal to some constant A, or P is equal to rho into the constant A. Rearranging this, we write this down as del P over del rho is equal to A. So if we have an ideal gas, then pressure P is related to the temperature T and density rho through relation P is equal to rho RT. If we take the differential of this one, then we have del P over del rho is equal to RT. Now using the early relation for the speed of sound, C as the square root of del P over del rho, that was at constant entropy S. Here that will be isothermal. We have a constant temperature T. Now this will be equal to putting the value of del P over del rho is equal to RT into this relation. We get C is equal to square root of R and temperature T, where we know that for air, this constant R, the gas constant, is equal to 0.287 kilojoule per kilogram and Kelvin, or we can write this down as 287.03 meters square per second square and degree Kelvin. Now on the other side, when we have the isentropic process, we have this famous relation that PV power gamma is equal to constant A, where gamma is the ratio of the two specific heat at constant pressure to the specific heat at constant volume. The value of gamma varies from one gas to another gas. For air, at standard temperature and pressure, or at room temperature, it is taken as 1.4. Rewriting this relation PV power gamma is equal to A, we can have P is equal to rho power gamma into the constant A. Taking the differential, del P or del rho is equal to gamma rho into power of gamma minus 1 into constant A, and we can rewrite this down as gamma rho minus 1 and rho power gamma and A. Or rewriting this in terms of the earlier relation that we have for pressure P, we can write down this: the change in pressure P with respect to the change in the density is equal to the ratio of the two specific heats into the pressure P divided by the density rho. So if we have an ideal gas, then once again P is equal to rho RT. So that would mean that delta P or delta rho is equal to gamma into RT, because P over rho is once again equal to RT. So rewriting this down into the speed of sound relation, we have speed of sound is equal to del P or del rho at constant temperature, and here it is at constant pressure. So if we take the square root of this one, we put the values from a relation over here, we get C is equal to gamma RT square root. And this is one of the important relations that we'll be using again and again in many of the exercises that follow. Okay, now we discuss the Mach number. Mach number is named to the scientist Mach, and it is basically the ratio of the speed of a fluid or an object in the stationary fluid to the speed of the sound and that fluid. So if we put the values of the C that we have obtained, just C as the square root of gamma or T for isentropic processes, where we had given R values is 287.03 meter square per second square in degree Kelvin, and gamma is 1.4 for air at standard temperature and pressure or at room temperature. Then the Mach number value could be written down as V over gamma RT. If we plot the values of the Mach number for different temperature and the speed, we can see that although the speed here is constant, the speed in the air is 350 meter per second, and because of the variation in temperature, we can see that the speed of sound changes. It's going from 300 up to 380, whereas the Mach number is changing is reducing as we go up in temperature, and the values could be more than 1 and could be less than 1. If the value of Mach number less than 1, then we consider that system to be subsonic. If it is approximately equal to 1, then it's transonic. Then if it is just 1, we call that system as sonic. If it's greater than 1, then the system is referred to as supersonic. But is very greater than 1, then the system is referred to hypersonic. Now let us recap quickly. The speed of sound is related to the variation in the pressure with respect to the variation in density at constant entropy. So this C is equal to the square root of del P or del rho at constant entropy S. An ideal gas case isothermal, then C is equal to the square root of R and T, where R is the gas constant. And isentropic process, C is equal to square root of gamma RT, where gamma is the ratio of the specific heats Cp and Cv, and the value of gamma for air at the room temperature at standard temperature and pressure is 1.4. So the Mach number, we can write this down as the ratio of the velocity of the fluid to the square root of gamma R and T. Let's solve one exercise. The exercise is taken from the book by Yunus Sanjal and Simbala. That's exercise 2.60. And this exercise, carbon dioxide gas enters an adiabatic nozzle at 1200 degree Kelvin with the velocity of 50 meter per second and leaves the nozzle at 400 degree Kelvin. The velocity of the carbon dioxide gas at the outlet has to be worked out. The gas constant of carbon dioxide is 0.1889 kilojoule per kilogram Kelvin. Its constant pressure, specific heat, and specific heat ratio at room temperature are given as 0.8439 kilojoule per kilogram degree Kelvin, and the ratio of the specific heat here is denoted by kappa, what we had denoted by gamma. So kappa is 1.288. Assuming constant specific heat at room temperature, you are asked to determine the Mach number at the inlet and at the exit of the nozzle. So we have to work out the Mach number at the 2 points, at the inlet, which is denoted by Mach subscript A1, and at the outlet is Mach subscript 2. At temperature T1 is 1200 degree Kelvin and T2 is 400 Kelvin. And the velocity at the inlet is given as 50 meter per second, and the outlet you had to work it out. And the properties of carbon dioxide at room temperature, we have the specific heat average at constant pressure as 0.8439 kilojoule per kilogram degree Kelvin, and the ratio of the two specific heats is given as 1.288. If we sketch the exercise, we have the carbon dioxide entering at one point here with velocity of 50 meter per second, and the temperature is 1200 degree Kelvin. At the outlet, we have the temperature is 400 degree Kelvin and the velocity is V2 meter per second, which we have to work out. We make certain assumptions in this case. We assume that carbon dioxide is an ideal gas. We also assume that the specific heat of the gas remains constant while going from a temperature of 1200 degree Kelvin to 400 degree Kelvin. We also assume that specific heat going from 1200 to 400 is the same as that given for the specific heat at room temperature, which is 0.8439 kilojoule per kilogram degree Kelvin. We also assume that the flow is steady, and we assume that the change in potential energy is equal to 0. And also, we assume that the specific heat ratio at the 2 points, gamma 1 and gamma 2, remains 1.288. Let's analyze now. We have a gas which is carbon dioxide and is entering a nozzle at a temperature of 1200 degree Kelvin with a speed of 50 meter per second, and is coming out at the other end of the nozzle at a temperature 400 degree Kelvin, and the velocity we have to work out, which is v2 meter per second. Now the relation for Mach number at the inlet could be written down as m subscript a1, which is equal to the velocity at the inlet divided by the square root of the ratio of the specific heat at the inlet and the gas constant R and the temperature at the inlet. Putting these values, we find out that the Mach value is equal to 0.0925, which is subsonic. At the outlet, once again writing down the relation, Mi2 is equal to V2 over the square root of gamma 2 RT2. Putting the values, we find out that the Mach 2 value is equal to 0.0032 multiplied by the velocity V2. Now, what is the velocity V2? We have to work out the velocity V2 from the energy balance relation. We have the total energy in the inlet that must be equal to the total energy at the outlet. Also, we assume no change in the potential energy, and the flow is steady. So we can write this down as H1 plus V1 squared by 2. So the microscopic and the macroscopic energy, potential energy being 0, is equal to H2 plus V2 squared divided by 2. So we write down V2 from this as equal to the square root of 2 into H1 minus H2 plus V1 squared. Remember, we have been given the average specific heat, which is 0.8439 kilojoule per kilogram degree Kelvin, and the average specific heat is equal to the fractional change in the finite change in the enthalpy over the finite change in the temperature. And this we can write this down as this the change in the two enthalpy. So we can write this down H1 minus H2. Delta H is, by the way, H2 minus H1, but we have rearranged the relation over here. So we have H1 minus H2 as Cp average into the temperature change T1 minus T2. So instead of T2 minus T1, we have written down T1 minus T2. So the minus on this side will cancel with the minus on this side. So putting the values, we work out that the H1 minus H2 value is equal to 675.12 kilojoule per kilogram. If you put these values into the relation, we get the value of velocity is 1163 meter per second. Compared to 50 meter per second, now here the speed is really huge. And if you look at the Mach number now, the Mach number is equal to 0.0032 V2. Putting the values, we get the Mach 2 value is equal to 3.72. As you can see that 1163 meter per second compared to the sound speed, which is about 340 meter per second, and this is really hypersonic speed that we get. Now for the next lecture, please come prepared. You can go through this topic in the textbook, which is article 2.6, and the textbook Fluid Mechanics Fundamentals and Application, and we'll be discussing viscosity, and we'll be talking about Newtonian and non-Newtonian fluids and the variation of viscosity with the temperature. Till then, I encourage you to post your questions related to the topic making full use of the KCMS facility that you have. Thank you very much.